I'd now like to talk about spatial data. With spatial data, this is one of our third of our three data types. There's tabular data, there's network data where we focus on the relationships between items instead of just the items alone. And now with spatial data, we're in the regime where we're thinking about data that is in some way directly tied to positions in space. This might be data that we sample in a field where we might have a grid of positions, whether that's a rectilinear grid or any other curvilinear grid or anything else, where there are attributes of data that are associated with spatial locations. Um, we might even have some sort of geometry, whether given or derived, which gives us exact things like locations of points along a boundary or of specific positions in space. Now, we're still in the regime of thinking about how it is that we encode data, particularly with spatial position and those other aspects of spatial layout. And in particular, we're thinking about using given spatial data rather than having spatial position be something that is completely determined by the designer of the visualization. So this idea that we should simply use the given spatial position data when we are visually encoding the data, well, when would we do this? It's when, first of all, we have such data, when the data set contains inherently intrinsically spatial attributes, and moreover, they are the primary thing. They are the most important thing in whatever tasks that we have to contend with. So typically those tasks are ones that revolve around understanding spatial relationships. Now, in this section of the video, I'm going to focus on geographic and cartographic data, and in spatial data 2, I'll focus more on the three-dimensional situations that we usually get with sensors or simulations. So, geographic maps. How do we want to think about these? Well, using the language of marks and channels that we've been learning in this class, what we have with a standard geographic map are polymarks, where there are relationships between the boundaries of these polys, of these two-dimensional area type segments, where they are touching. So we do have shared boundaries, but they are not overlapping. They're specifically touching rather than overlapping. Here we see a geographic map on the right side, a standard world map. Now, what's going on here? In this case, this actually is a rectilinear layout. We have latitudes and longitudes, and those are mapping to XY positions in space. As I'll get to at the very end of this video, there are other projections. It doesn't have to be rectilinear, although things like the Mercator projection are rectilinear. So what is going on with the channels? Well, we're taking given spatial data and we're simply using it. And what that means is that the shape of the poly simply encodes a geographic boundary, and the area of the poly does encode another known quantity. It's the land area of the actual geographic region. So this is what it means to use spatial data. We have shape and area given to us, and those are simply what we show in those marks. Now, where it gets interesting from a visualization point of view is what the cartography community usually calls thematic maps. They use the word theme to mean the spatial variability of an attribute. And so what we do is we combine that map, like we saw on the previous slide, a geographic map or a base map or a reference map, with some typically simple flat table of data. And what that means is we have these two things that we're joining. One is that those marks, like we just saw in the previous channel, those touching boundary polymarks, they show geographic regions, provinces or countries or states or anything like that. So we have that sort of base geographic data. We might also have point marks if we're showing things like cities and we're zoomed way out. So any kind of a specific location can also be shown with a point mark or with the polymark. But then in addition, what we have is we have a table of data where for every one of those regions where we have a geographic boundary, we also use that region ID as a categorical key in a table, and we look up some value. So those value attributes are indexed according to region treated as a categorical key attribute, in addition to a region being represented by a complex boundary that forms a polymark. Now, there's a lot of standard ways to show maps, and the ones I'm going to talk about in detail today are choropleth, symbol maps, cartograms, and dot maps. So let's get going. So choropleth map, that's just a fancy word for a map where we color code stuff in the geographic regions. So we're using given spatial data, and we would do this when, as I said before, the central task is understanding spatial relationships. So what is the relationship between these attribute values and the spatial locations of all of these regions? So from the data, we do have this geometric data that we're given, which are the boundaries of these polys. And we then also have a table where for every one of these regions, we look up a single quantitative attribute. Now, what's going on here? Well, just like we talked about in that previous slide, we do have these polymarks. And so they're touching, they're not overlapping the boundaries of these. The shape is the geographic boundary, the area encodes the geographic area. Typically, we could even think of the shape as being primary, and then what falls out of that is the geographic area. Those two things in this case, of course, are correlated. And in this case, and in many other cases, particularly when you're looking at a smaller region than the entire world, we treat the global layout as rectilinear because we just think of latitudes and longitudes as x and y positions on a rectilinear plane. And then the key thing is we are encoding the quantitative attribute with color, right? In this particular example, our color map is sequential, right? We're showing things from small to large. It's segmented where we see discrete different regions in the color map. But you could also have choropleths where you have a continuous color map. That's completely legitimate as well. And the key thing is in this map, there is only one mark type. There are only the polymarks of the base map. And the encoding that shows us that quantitative attribute is a color coding. Now, one thing to be careful of is population maps have a real issue, which is they're correlated with where people live and what the attribute shows. And as this snarky XKCD comic shows, there's a whole bunch of spurious correlations because almost every attribute you might imagine is highly, highly, highly related to simply showing where people live. So what you often would want to think about when you're using a choropleth map is normalizing by the density of the population in each region. If you simply encode the raw values, you're just seeing population maps. You're not actually seeing the particular attribute you care about. If you normalize, so you say things like to show unemployment rates, you show unemployed people per 100 citizens, or mean family income. Use something to normalize against so that you're not just seeing where people live. Now, this is not just an issue about choropleth maps or even just about maps. In general, the question of when should you use absolute counts versus when should you do some sort of normalization so you're seeing relative proportions, this is intrinsic to a lot of visualization design decisions. And the failure to normalize is a very common error. So it particularly hits people with choropleth maps, but be aware of this in general in visualization design decisions. So with choropleth map, well, we can definitely use it if we need to understand spatial relationships. Notice how we're only seeing one thing at once. We are color coding, right? We're using all of hue and saturation and luminance to show one attribute at a time. Be very careful to normalize when that's appropriate. Think hard before you don't normalize. You almost always do want to carefully consider normalization. Now, also, you want to be careful when you're choosing what colors to use and when you're using the number of bins. If you're discretizing your attribute into a discrete number of levels, think carefully about that because the kinds of patterns you see are going to be highly dependent on both your bin size and your specific choices of color. The very best case for choropleth maps is when the regions are roughly equal sized. So what's good about them? What's bad about them? The good thing is, first of all, they're very easy to read and understand. You typically you might need a legend to show some of the details, but the basic idea that you're color coding something, people pretty much universally get without any need for training. So it's well established. You don't need to have any kind of a teaching cycle. Also, the way in which a lot of data is collected and aggregated is according to geographic regions. So if the way you want to show it and the way it's gathered match up, that gets rid of a whole suite of problems. What are some of the downsides? Well, We've talked a lot in this class about how the most effective visual channel is about spatial position, and in some sense, you're using it just for showing the geographic locations. So if those geographic locations are central to your question, if understanding the patterns of spatial distributions is your most central tasks, then that's completely reasonable. If some other aspect of the data were more important, then it could be that maps are not the best way to show that. Now, that's true not only for choropleth maps, but in general for looking at spatial data in a geographic way. Now, something that is specific to choropleth maps is that the visual salience of the color coding completely depends on the region size. Remember that with color, small regions, we are less able to perceive color than with larger regions. And so the amount that we notice it depends on how big the region is, but that might not be the importance with respect to the value of the attribute. Maybe a very small region has a very high value, but it's so small that there's not much of that color, so you don't get that visual pop-out effect. So what that means is with choropleth maps, large regions appear to be more important than smaller ones, and in some cases, that is not what you want to get at in your data analysis. Also, as I mentioned on the previous slide, the color palette choice does have a very large influence on the result, so you have to be aware of that. So what else could we do? Well, we could use symbol maps. Now, symbol maps are an entire family of idioms where, as the name suggests, we use a symbol to represent aggregated data across the entire region. It could be a point mark, it could be a glyph. So now we have a two-level interpretation of the data. The first level is simply that geographic map, which we're using as polys as a base level. And then based on that, we do something else at the next level up. We'll call that level 2. So one symbol per region on the base map where we must use the same global layout for these extra marks as for the base marks. So as I said before, typically that's rectilinear. Now the key thing is we compute things typically the centroid of that poly on the base map. That's why this relies on that base map. And then we're positioning the symbol according to that. And since we're using position, that means that order comes along with it. Now, typically the symbol, particularly if it's a circle, but in general, we're often just using one attribute to size code that symbol, which means we're typically using a polar local layout where we're using the radial span to size code according to that attribute. Typically with a symbol map, these symbols are uniform, right? So on the bottom left, we see a circle coding. And the color could encode data, could be uniform. Now, circles cannot be orientation coded, right? They're symmetric. But if we had an asymmetric glyph, like the one we see with this Christmas tree map on the lower right, then you could, in fact, choose to orientation code if you have the ability to see because the glyph is asymmetric. Sometimes these symbol maps are called proportional symbol maps or graduated symbol maps, but these can be a good alternative to choropleth maps. Here's a couple examples of symbol maps with more complex glyphs. Here you see we're basically using little mini bar charts on the left, little mini pie charts on the right. The point being that what you put in each geographic region could be more complex than just a single mark. And notice how in these examples with the glyph maps, the size of the glyph tends to be uniform because what you're doing is you're not size coding with the entire thing. It's the little marks within each glyph that actually tell you information with their sizes. There's alternatives. For example, necklace maps are a nice algorithmic alternative where instead of putting the symbol in the centroid of each region, you try to algorithmically compute their layout in a ring around a whole section of the map to try to make it more clear what the relationship between them is, and then you don't get this problem with occlusion. So we have a necklace map on the left and then a sort of straight up symbol plot with colored circles on the right. So what's good about symbol maps? Well, they're pretty intuitive to read and understand. We often don't need a lot of explanation for those either. And what they do is they address this problem of the disparity between the size of the region and the salience of the data, because that symbol, well, it follows the attribute value, not the size of the region. So as I said, typically we can even just use a uniform size if we're dealing with glyphs rather than with size-coded point marks. Okay, so what's the downside? Well, the obvious one is things can overlap each other, right? The symbols could overlap each other, making it harder to see. They could overlap the boundaries of those low-level regions. So both of these then can give rise to issues of interpretation simply because of visual clutter. If you have complex glyphs, you might need either just a simple legend or some kind of explanation or training to get people to interpret those. What else could we do to a map? Well, we could change things. So a cartogram is a family of idioms where all the polymarks on the map are changed simultaneously, all at once. So we don't add a new mark, we change that existing mark. We still have a bunch of polys, but we've replaced them with new ones. So this is now I've talked a lot about how if the boundaries of polymarks or any other marks are touching, well, you can't just change one, but you can change them all. If you change them all at once and compute new values, then you had the original map where you had these touching boundaries, and you compute a new map where you also have touching boundaries. So in some ways, the way that the old marks interlocked, the new ones interlock. And typically, we're trying to preserve something. We're trying to preserve the relative position as much as we can from the old layout to the new one. Now, there's a lot of different variants of cartograms, and I'll talk a few of these. And you can think of these as different constraints on the algorithm that you're employing to do this. One flavor is that we try to preserve the actual shape of the mark as much as possible. And then we are encoding this new quantitative attribute with the area of that. And we do our best to preserve the shape. Another approach is we say, well, actually, we're going to throw away the shape. We're going to regularize to a completely uniform shape for each region. And then we're going to encode something with color, much like we do with choropleths. Or we could go even further, and not only do we regularize the shape, but also the size. So let's look at some examples. So that first kind, a contiguous cartogram, sometimes these are called area proportional contiguous cartograms, is where we just actually make this new set of polymarks where we try to keep the shape as much as we can, but that's a soft constraint. The hard constraint of the algorithm is we must have the total area that is surrounded by that boundary. It has to encode this new quantitative attribute, which means that the shapes might actually change quite a bit because also the algorithm preserves the property that all the mark boundaries touch each other. So you can see a couple examples here where a world map has been made into a contiguous cartogram according to two different attributes. On the top, it's greenhouse emissions. On the bottom, it's child mortality. And notice how the areas of these country marks are really different from each other, but it's preserving the fact that they all touch. And of course, in this case, because these are both pretty extreme examples of attribute value ranges, we have massive distortion of those original shapes. So you can think of this as if you wanted to think about how the algorithm would do that, you give it as input the quantitative attribute, which is this new target size. You try to keep the shape as close as possible while actually making the area vary according to this new attribute. Now, typically what you're trying to do in these kinds of algorithms is the absolute position is off the table. You definitely can't count on that to be true, but you try to preserve the order, the relative positions, particularly about geographically meaningful things like east-west and north-south relationships. So we wouldn't put Canada below the United States. We would want to keep it above the United States because that's preserving a north-south order relationship. Now, what else could we do? As I said, we could completely throw the shape away. We could simply regularize all shapes to a circle. Now we've gone from shape, as we have in polys, to simply a symbol, which means we're now dealing with point marks. But we have point marks where we want to make sure that those boundaries touch. So we inherit the same global layout from the original. So typically, as in all these examples, we're looking at something rectilinear. And now what we've got is we've got a bunch of point marks that are size coded, and Since they're circles, we're doing the common thing where our local layout is polar and we're just using the radial span to size code these point marks. Now, with this idea that we have varying rather than encoding um, semantics for the marks, well, the order is algorithmically computed. It's a very strong constraint. We try very hard to preserve that relative ordering. We try less hard to preserve the absolute position. It's a looser constraint. So it's trying to be as close as possible to those absolute geographic locations of the given spatial data we started with. But in both cases, for both order and position, these are algorithmic computations that are not in any way guaranteed to absolutely simply encode um, a target attribute, whereas their size does encode. Their size actually has a value that can be decoded by our perceptual system. But the order and the position, those are just, best effort hopes to preserve algorithmically. And that's why they're varying rather than encoding. Now, what's uniform here? Well, orientation's uniform. The circles are symmetric, so we can't possibly orientation code anything. And by definition, with a Dorling cartogram, the symbol is a circle. So of course, we're not going to be symbol coding this. They're all circles. You could use color to encode something, or it could be uniform. In this case, the example here is encoding, obviously. So for those of you who are aware of the mathematical idea of a circle packing algorithm, this is just a special case of circle packing where you can think about the positional constraints as being quasi-geographic, right? They're inspired by the geography, but that's not guaranteed to be kept. It's just preserved as much as possible, given those other hard constraints of touching point marks of specific sizes. What else could we do? Well, we could actually regularize both the shape and the size. And then typically what people do is they arrange them in some form of grid. Sometimes these are called equal area cartograms or grid cartograms or mosaic cartograms or pseudo-Deimers cartogram or geofacets or geogrid or tile grid heat map or tile grid map or tile map. These many names all refer to the same basic idea, which is we do abstract things down to new point marks that do touch and they don't overlap, but we've made a lot of things uniform. We've made the size uniform as opposed to the previous example. We've made the symbol uniform within any given one of these cartograms. We make the orientation uniform. So there's versions of these, as you can see, that you pick different shapes for the entire thing. You could have circles, you could have squares, you could have hexagons. So just like with the other one, what we're doing is we've got an algorithm that varies the order and the position with different amounts of constraints on it. The hard constraints is we have to align positions to some sort of grid. So that's a hard constraint. And then the preserving the relative order, I'll think of as a medium constraint. And then the absolute position is a softer constraint. So we do as best as we can, but the positions might be quite different. And just like with the others, um, if you're using a equal area, size, and shape, then, well, you can't encode with size, right? And so what that means is necessarily we're doing the same thing a choropleth does. We're encoding the attribute with color. So you can think of these as a cartogram mixed with a choropleth, because that's exactly what we are doing here. These have become quite popular for showing electoral results because they're arguably the easiest to interpret of all of the families of cartograms. So if you're seeing cartograms, particularly in a data journalism context like a newspaper with election results, these days many of them are these grid cartograms. Now we could go further. We could actually have a multi-level cartogram where within the cartogram, what we see are these little unit boxes. So the shapes of the geographic regions are made by combining an integer number of these little unit marks. So just like we saw with tabular data with this idea of multi-level shapes made out of unit marks, we have to interpret this at two levels. In this case, the geographic region, which are the 50 US states, these are shown as polymarks, right? These need to be interpreted as a two-dimensional area mark. And then at the bottom level, we just have these little unit marks, which are all the same size and all the same shapes, right? They're uniform. They are, in this case, they're squares. Now, what this gives you What the benefit of these is you can actually, if you wanted to, count the number of boxes in these states. It gives you countability. Now, counting is not something we can do with this sort of immediate perceptual pop out like we have gotten with some of the other visual encodings, but with cognitive effort, it can be decoded from the image, which is a different layer of interpretation of a visualization. Now, there's one nuance here. It's pretty clear that we have touching marks in the map on the left. So just like with all cartograms, there's this constraint that all of the marks touch each other. Now, you might say that the map on the right, they're not touching. There's a subtle thing happening here where the amount of white space is actually precise here. In some sense, it's the inverse of the population density, and it's particularly clear when you start looking at some of the states that are close to each other in the New England version of the U.S. on the upper right, where you really can treat those areas as countable boxes that are white rather than countable boxes that are colored. So in this case, we are still thinking of this as touching marks. We just have two kinds of marks, colored boxes and white boxes. This is a strange special case compared to the usual, though. So with a contiguous cartogram, the pros and cons are people definitely can get intrigued by it and they can engage with it. And if there are real large and surprising size disparities, that tends to be when they're best, particularly if a relatively either a small number of things have these disparities or the disparities are grouped by region. Now, the downside is you have to know what the original map looked like, or you don't have any context to understand what changed. So you need substantial familiarity with the original data set, and you are using the memory of the person of the original compared against what they actually see before them. Um, Now, one of the ways to mitigate that, for example, is to have animated transitions back and forth between the original and the cartogram, or to show them side by side to try to help people use their eyes rather than using memory. Now, also, really major distortions can simply be problematic. I mean, they're literally aesthetically displeasing. They are strangely ugly in many cases. And in the extreme case, you might not even be able to recognize what the mark is supposed to be. So there are problems from major distortion. And certainly there's a loss of precision, a loss of accuracy. It's difficult to extract exact quantities. If you wanted to do that, this would not be the right idiom. So that's for those contiguous cartograms we saw first. What about the non-contiguous ones? Well, definitely they're easier to understand than the contiguous one. These sort of stylized marks where we regularize shape or we regularize shape and size are substantially easier to understand. And we can basically combine them, right? Particularly if you've got an equal area one where all those shapes are uniform, then you basically have, you can put a cartogram on top of that. You can color code. But the good thing is, if you do have an equal area approach, it solves that problem we had with the choropleths. Um, so it so the choropleth map where you had size disparities, well, you no longer have size disparities. You've made every geographic region equal sized. So this is a great thing. Now, you do still need some familiarity with the original data set. Again, it's alluding to the idea that if you had no idea what the geographic region was, it might be problematic. So you still might need to explain something about this quasi-geographic positioning. And the great thing about equal area cartograms is also the terrible thing about them. They make everything equal size. But if the original map had really, really different sizes, then that might introduce very substantial distortions as when you have to fit them together into some grid. So if the sizes are really disparate, then you might get very large distortions of spatial position, and maybe even not be able to preserve the ordering constraints that you would like. Okay, what else could we do? We could put dots on a map. So unsurprisingly, we call that a dot map. An important thing is there's two very different kinds of dot maps. And let's start with the easy to understand one, which we'll call a one-to-one dot map. And that's where there's a thing that you want to show on a map and you put a dot at the location of the thing, right? The thing is, let's call it an item or a feature or a phenomenon. So sometimes people call these dot density maps. Sometimes they just call them dot maps or one-to-one dot maps, which I think is the least confusing name for these. So in this case, a point represents an item and it is uniform. So the size of the dots are uniform. The symbol is typically uniform. In this case, it's circles. You can color code, or that could be uniform. And what we've done here is we now have two different levels, but they're two different mark types, but they're at the same level. One doesn't depend on the other because you actually are placing these dots at locations, in some sense, independent of where that base map was. So we have the dot points and we have the region polys, and these are at the same level. There's not a dependency. There is a correlation, there's a relationship between them. And it's interesting to see which, in this case, state boundaries the exact dot location falls within. But there's not a dependency. You could calculate one without knowing the other. So what people typically do for this is showing, the example is showing the nearest burger chain from a set of 2, 4, 6, 7 options. Um, the task is to do things like identify distributions that are spatial and identify patterns or clusters or outliers. And we can do all these things from this map. Now, in addition, um, there are these dot density maps or dot distribution maps. And this is, I'm going to call this a many-to-one map. And so what they're doing is they are using dots to show, with the density of dots, to show a quantitative attribute. And in this case, one symbol represents a constant number of items. Like in this case, one dot is for 50,000 people. Um, and all of those dots do have uniform size and symbol and orientation. But the key thing is position doesn't directly mean something. It is randomly generated within the region to correspond to the density of the phenomenon. So just like the first example, we have two mark types at the same level. But the key thing is the actual exact location of those dots does not mean something. They're just trying to represent densities. So we can see high-level spatial patterns and clusters, but this point can be quite confusing, particularly if you don't know whether to interpret this as a dot density map or a one-to-one map. So looking carefully at the legend, I mean, the legend does communicate this idea, but if you just looked at the map itself, that might not be obvious. So the pros and cons, the one-to-ones are very straightforward to understand, and it also avoids this sort of region size issues with choropleths. Um, Now, just like with choropleths, though, the same problem of normalization holds. I mean, we were literally just looking at a population map, but if we also wanted to see something else, that would similarly be highly correlated with where people lived. So you want to be careful with normalization just as much with these one-to-one dot maps as you do with choropleths. Certainly, much like some of the other cartograms we saw, you're not going to be able to simply extract quantities in a really easy way with those dot density maps. Um, if you think about implementing these, just be aware suddenly you're drawing a lot of dots. These can be quite slow, so there are some performance issues as well. And as I said, if you think that the position of the dots are meaningful in those many-to-one density maps, that can be extremely confusing. So we've now walked through four major kinds of thematic maps. And it's very common to mix and match all of these design elements, right? Anything can be combined with a choropleth. You can use cartograms with these other approaches. For example, and you must use it in some cases, like with the equal area cartograms. So we could take a cartogram and add a symbol inside that. That's a possible combination. We could put dots in cartogram regions, although that gets a bit tricky, but it's not impossible. Particularly with dot density maps, it would be much easier to do that as opposed to one-to-one dot maps. Now, typically we don't combine symbol maps and dot maps because that would just be confusing. Would a point mark be interpreted as a symbol, right? That aggregate one for the whole region, or should it be interpreted as a one-to-one dot of a meaningful position representing a very specific item of data, or those many-to-one dots where just the density of the dots represents a quantity? So typically we wouldn't combine those two. Now, finally, let me talk just briefly about map projections. I've been sort of waving my hands and not talking about them explicitly. I've just been showing you maps and I haven't exactly said what's going on. So a map projection is a mathematical function that maps the three-dimensional surface of the Earth to something that is flat in 2D. And necessarily, something has to give. Any projection of the sphere onto the plane must distort it in some way. imagine that you took an orange peel and you try to smash it down on a table flat, right? Something has to give. In the case of an orange peel, typically it sort of splits apart. It doesn't preserve contiguity. And in fact, you can't have all three things. You could either have the area of the regions be correct, or the angles stay correct, or it could stay contiguous. But it is mathematically impossible to have all three at once. And so the space of possible maps has been heavily, heavily explored. There's a lot of discussion of the choice of should you have your area correct of your geographic regions or your angles correct. But there are also a lot of map types that give up on contiguity. Here in this figure from the myriahedral projections paper by Jaak van Wyk, we see the Mercator projection in the bottom right, and then we see some other alternatives. And in some where we have the area equal, in others where conformal is a fancy math word for keeping the angles correct. And so in Mercator, we have correct angles, whereas in some of the others, we have correct area. So as I said, the Mercator projection, although it's extremely well known, it does not preserve the areas. It was actually designed for navigating ships where you wanted it to be easy to get the angles right. And so the areas can be very wrong. Now, if you're just looking at an individual country, it's usually not a huge problem. But if you're looking at an entire world map, then these country sizes get highly distorted, particularly when you get close to either the North Pole or the South Pole. And as you can see with the example on the left, once you get all the way to the poles at Antarctica, right, that shows Antarctica is gigantic. And of course, it's not nearly so gigantic. So here on the right, we have an example of the true size of countries. And you can definitely see that bias as we get closer and closer to the North Pole, just given where things are laid out in relation to North and South Pole. Canada, of course, is substantially smaller than its true size. Now, a key point is this we can very much think of as a rectilinear global layout. Notice how in the map on the left where we see grid lines, right? And they're clearly rectilinear. So to a first approximation, I often talk about geographic maps as having a rectilinear global layout, particularly for most of the commonly used ones. That is the case. But there are many, many, many projections out there in the world. Mathematicians have developed a huge number. Some of them are rectilinear, some are polar, or the 3D version of polar, sometimes called stereographic projection. But there's a whole lot that are not either one of them. So in our way of thinking about global layouts, we would simply call those other. So here you see many, many examples that do not map easily to either rectilinear or polar. There's a whole lot more if you're interested in exploring. Here's a couple of fun websites where you can actually see interactive transitions between some of these different map types, which helps you understand a bit more what's going on with the mathematics of the projection. All right, and with that, we are wrapping up geographic maps.